Chapter 5. Sources of Electricity. Every student knows the story of Benjamin Franklin and his kites. For centuries before Franklin, scientists and philosophers had observed lightning. It was thought the experimentation and research of Franklin that the relationship between lightning and static electricity was confirmed. What is electricity, and where does it come from? Years before the discovery of the electron theory by J.J. Thomson, it was suggested by Franklin that electricity consisted of many tiny particles, or electric charges. He further theorized that electrical charges were created by the distribution of electrical particles in nature. We have learned that a potential difference or electromotive force is created when the electrons are redistributed. A body might assume a charge; its polarity is determined by the deficiency or excess of electrons. People have turned their scientific interests in research to the development of machines and processes that can cause an electrical imbalance and an electrical pressure. There are 6 basic sources of electricity or electromotive force. They are friction, chemical action, light, heat, pressure, and magnetism. In this chapter we will discuss in detail producing electricity from chemical action or batteries. You will also learn how electricity is produced using light, solar batteries, pressure, and heat. 5.1. Chemical action. One of the most familiar sources of an electrical potential or voltage is the battery. In 1790, the Italian scientist Luigi Galvani observed a strange phenomenon during the dissection of a frog supported on copper wires. Each time he touched the frog with his steel scalpel, its leg would twitch. Galvani reasoned that the frog's legs contained electricity. Alessandro Volta, another Italian scientist, invented the electric cell, named in his honor, called the voltaic cell. The unit of electrical pressure, the volt, is also named in his honor. Volta discovered that when 2 dissimilar elements were placed in a chemical that acted upon them, an electrical potential was built up between them. Thus, electricity can be produced by chemical action. The student can construct several voltaic cells to demonstrate this action. Cut a 1-inch square of blotting paper and soak it in a strong salt solution. Place the wet paper between the penny and the nickel as shown in figure 5-1. If a sensitive meter is connected to the coins, it will indicate that a small voltage is present. In figure 5-2, electricity is created using a grapefruit. Make small cuts in the skin of a grapefruit. In one cut, place a penny. In the other cut, place a nickel. Once again, a meter will indicate that a small voltage is present. A better cell can be made by placing a carbon rod. These may be removed from an old dry cell and a strip of zinc in a glass jar containing an acid and water solution. In figure 5-1, a simple cell is produced using a nickel and a penny and a salt solution. In figure 5-2, a grapefruit can be used to produce enough electricity to operate a small radio. Lesson in safety. When mixing acid and water, always pour acid into the water. Never pour water into the acid. Acid will burn your hands and your clothing. Wash your hands at once and clean water if you spill acid on them. Acid may be neutralized with baking soda. See your instructor for first aid. Figure 5-3. This experimental cell made with zinc, carbon, and acid produces enough electricity to power the light. When the polarity of the carbon rod is tested, it will be positive. The zinc strip is negative. If a wire is connected between these 2 elements or electrodes, a current will flow. A voltaic cell can be described as a way of converting chemical energy into electrical energy. The zinc-carbon example of a voltaic cell, the sulfuric acid H2SO4 and water H2O solution, is also known as an electrolyte. When the electrodes are placed in this acid electrolyte, a chemical action takes place. The sulfuric acid breaks down into the positive ions 2H plus and negative ions SO4 2 to the negative. The negative ions move toward the zinc electrode and combine with it by making zinc sulfate, ZnSO4. The positive ions move toward the carbon electrode. This action creates a potential difference between the electrodes. The zinc will be negative, the carbon will be positive. This cell will develop about 1.5 volts. If a load such as light is connected to the cell, a current flows and the light glows, as seen in figure 5-3. As the cell is used, the chemical action continues until the zinc electrode is consumed. The chemical equation for this action is Zn plus H2SO4 plus H2O is transferred to ZnSO4 plus H2O plus H2, which increases. Zinc plus sulfuric acid plus water chemically reacts to form zinc sulfate and water and free hydrogen gas. This cell cannot be recharged because the zinc has been consumed. Primary cells. The zinc carbon cell described in what is known as a primary cell. A primary cell is a cell in which the chemical action cannot be reversed. A primary cell cannot be recharged. Defects in the primary cell. One might think that the chemical action of the zinc carbon primary cell would continue to produce voltage as long as the active ingredients of the cell are present. In studying the equation for the discharge of the cell, you will observe the formation of free hydrogen gas. Since the carbon electrode does not enter into chemical action, the hydrogen forms gas bubbles. These collect around the carbon electrode. As the cell continues to discharge, an insulating blanket of bubbles forms around the carbon. This reduces the output and terminal voltage of the cell. The cell is said to be polarized. The action is called polarization. To overcome this defect in the simple voltaic cell, a depolarizing agent can be added. Compounds that are rich in oxygen, such as manganese dioxide, MnO2, are used for this purpose. The oxygen in the depolarizer combines with the hydrogen bubbles and forms water. This chemical action appears as 2MnO2 plus H2 transferred to Mn2O3 plus H2O. The free hydrogen has been removed, so the cell will continue to produce voltage. One might assume that when the current is not being used from the cell, the chemical action would also stop. However, this is not true. During the smelting of zinc, not all impurities are removed. Small particles of carbon, iron, and other elements remain. These impurities act as the positive electrode for many small cells within the one large cell. This chemical action adds nothing to the electrical energy produced at the cell terminal. This action is called local action. It can be reduced by using pure zinc for the negative electrode or by a process called amalgamation. With amalgamation, a small quantity of mercury is added to the zinc during manufacturing. As mercury is a heavy liquid, any impurities in the zinc will float on the surface of the mercury, causing them to leave the zinc surface. This process increases the life of a primary cell. Types of primary cells. There are many different primary cells. What follows are details on some of the most common primary cells you might encounter. Zinc carbon cell. Although the primary cell has been described as a liquid cell, a liquid is not used. Rather, the primary cell is often a dry cell. In a dry cell, the electrolyte is in a paste form as opposed to a liquid form. A dry cell averts the danger of spilling liquid acids. Flashlight battery cells are examples of dry cells. The dry cell consists of a zinc container that acts as the negative electrode. A carbon rod in the center is the positive electrode. Surrounding the rod is a paste made of ground carbon, manganese dioxide, and salt ammonium chloride. Mixed with water, the depolarizer is the MnO2. The ground carbon increases the effectiveness of the cell by reducing its internal resistance. During discharge of the cell, water is formed. You may recall having difficulty removing dead cells from a flashlight. This is because the water produced caused the cells to expand. Although this problem has been resolved by improved manufacturing techniques, it is still not advisable to leave cells in your flashlight for long periods of time. You should keep fresh cells in your flashlight so it will be ready for emergency use. Lesson in safety: improper battery use can cause leakage and explosion. Therefore, obey the following precautions. Install the batteries with the positive and negative polarities in proper direction. Do not use new and old batteries together. Never attempt to short circuit, disassemble, or heat batteries. Do not throw batteries into a fire. Batteries do contain dangerous materials that should be recycled or disposed of properly. Contact your local recycling facility or fire department for more information. Alkaline cell. The alkaline batteries use manganese dioxide for the positive activating substance. Zinc powder is used as the negative activating substance. A caustic alkali is used for the electrolyte. Recent progress in electronic product design has demanded more compact supply sources. The number of products needing a large current and a long battery life have increased. This required the development of more advanced batteries. Cylindrical alkaline batteries are now widely available, widely used to supply power for electronic products. They can be used with common manganese dioxide batteries. See figures 5-4 and 5-5. Mercury cell. A relatively new type of dry cell is shown in 5-6. It is called the mercury cell. It creates a voltage of 1.34 volts from the chemical action between the zinc negative and the mercuric oxide positive. It is costly to make. However, the mercury cell is better in that it creates about 5 times more current than the conventional dry cell. It also maintains its voltage under load for longer periods of operation. The mercury cell has found a wide use powering field instruments and portable communication systems. See figure 5-4, the AA alkaline cell, and figure 5-5, a cutaway of the AA battery size alkaline cell. The lithium cell. Lithium has the highest negative potential of all metals. It is therefore the best substance for an anode. Many battery makeups are possible by mixing lithium with various cathode substances. Energy densities of these batteries can be computed by respective reaction equations. Figure 5-7 shows the energy densities of lithium batteries compared to those of conventional batteries. Lithium is the most suitable anode for production of high voltage and lightweight batteries, referred to figure 5-8. In figure 5-6 we see a mercury cell. It creates a voltage by chemical action between the zinc and the mercuric oxide. Features of lithium batteries such as voltage and discharge capacity are determined by the type of cathode substance used. Fluorocarbon is an intercalation inserted between or among existing elements compound. It is produced through reaction of carbon powder and fluorine gas, and it is expressed in CFN. The silver oxide cell. Silver oxide cells have several advantages over other types of cells. These advantages include very stable discharge voltage, excellent high discharge characteristics, high energy density per unit volume, wide range of operating temperatures, compact thin size. The compact silver oxide batteries have the highest electrical volume and leakage resistance of any battery of that size. They are commonly used in watches. 2 types of silver oxide batteries are made for use in watches. One type uses caustic potash for electrolyte. The other uses caustic soda. The caustic potash battery has the symbol W on the bottom of the battery. It is for high drain use, where more power is needed. It is used with wristwatches with liquid crystal displays and multifunction analog watches. The caustic soda battery has the symbol SW on the bottom of the battery. It is for low drain use. It is used mostly in single function analog watches. Figure 5-9 shows a cutaway of a silver oxide cell. Nickel-cadmium cell. The nickel-cadmium cell is a rechargeable dry cell. Basically, these are nickel-cadmium alkaline batteries with paste rather than liquid for the electrolyte. The ability to be recharged is just one of their advantages. Other advantages include long life, high efficiency, compactness, and lightweight. The nickel-cadmium cells produces a high discharge current due to its low internal resistance. Other uses include the powering of small radios, burglar alarm systems, camera flashes, and aircraft instruments. See figure 5-12, the construction of a nickel-cadmium cell. One type of nickel-cadmium cell uses a positive and negative plates, a separator, alkaline electrolyte, and a metal case, and a sealing plate with self-releasing safety vent. It is shown in figure 5-12. The positive plate of this battery is a porous powdered nickel base plate. It is filled with nickel hydroxide. The negative plate is a punched plate of thin steel coated with cadmium active material. The separator is made of polyamide fiber for high temperature uses. It is made of a non-woven polypropylene fiber. The positive plate, separator, and negative plate are pressed together, wound into a coil, and inserted in the metal case. The electrolyte is an alkaline aqueous solution. It is totally absorbed into the plate and the separator. The metal case is constructed of nickel-plated steel. It is welded on the inside of the negative plate. It becomes a negative pole. The sealing plate uses a special liquid sealing agent to form a perfect seal. The positive plate is welded on the inside of the sealing plate. It becomes the positive pole. The self-resealing safety vent permits the discharge of the gas in the event of an abnormal increase of internal pressure. This prevents against rupture or other damages. The vent is made of a special alkaline and oxidation-resistant rubber. This ensures that operating pressure and safety features will be retained over a long period of time. The electromechanical processes of a nickel-cadmium alkaline cell are outlined below. See the formula at the bottom of page 89. In this process, charging and discharging are reversed in a very efficient manner. The electrical energy used during discharge is regained during the recharge. During the final charging stage, an oxygen gas is created with the reaction occurring at the positive. See the formula at the top of page 90. This oxygen passes through the separator to the negative. After this, an absorption reaction takes place at the negative and absorption occurs. See the formula again at the top of page 90. Nickel metal hydrate cell. Nickel metal hydrate, or NiMH, is a rechargeable battery very similar to the NiCad or nickel-cadmium battery. The NiM battery uses the nickel for the positive cathode and a hydrogen absorbing alloy for the negative anode rather than cadmium, which is found in the NiCad battery. The fact that NiM batteries do not use cadmium makes them environmentally friendly. Hydrogen absorbing alloys are made from combinations of nickel and iron, Fe, magnesium, Mg, and lanthanum, La. The alloys can absorb large volumes of hydrogen equal to approximately 1,000 times their weight without an increase in volume. This means the batteries can be sealed without the danger of explosion caused by expansion of materials. A NiM battery can have 2 to 3 times the storage capacity of a NiCad battery of equal size. This has made it an excellent battery for hybrid vehicles and portable computer applications. The discharge voltage level is 1.2 volts, which is the same as for NiCad batteries. The NiM batteries can be recharged over 500 times. The combined characteristics of the NiM battery makes it an ideal replacement for existing NiCad battery applications. NiM batteries should never be completely discharged. If they are, one or more of the cells can reverse polarity, which will result in permanent damage to the battery. Electronic devices that use NiM batteries typically have a special circuit designed to detect low voltage levels and then disconnect the battery circuit before damage can occur. Batteries in series and parallel. Often a single cell is called a battery. By strict definition, however, a battery consists of 2 or more cells connected together. These cells are enclosed in one case. Series connection. In the study of electricity, it is important to understand the purpose and the result of connecting cells in groups. First, consider the series connection. In this method, the positive terminal of one cell is connected to the negative terminal of the second cell. In figure 5-13, 4 cells are connected in series. The output voltage will be equal. See the formula. E out equals E one cell times N, where N equals the number of cells. So, in the case of the battery shown, voltage out equals 1.5 volts times 4 equals 6 volts. Notice that the voltage has increased 4 times. However, the capacity of the battery to supply a current is the same as one cell. Cells are connected in this manner to supply higher voltages for many uses. A flashlight may use 2 or more cells in series. Batteries for portable equipment have many cells in series to produce 6, 9 to 24 volts. The amperage does not increase by connecting cells in series. Parallel connection. In figure 5-14, the positive terminals have been connected together and the negative terminals have been connected together. These cells are connected in parallel. The voltage across the terminals of the battery is the same as only one cell. Although the voltage has not increased, the life of the battery has been increased. Because the current is drawn from all cells instead from just one, the amperage is added by connecting cells in parallel. See figure 5-13 now. Schematic diagram of 4 cells connected in series. The voltages add when connected series. And 5.14, schematic symbols, a pictorial and schematic diagram of 4 cells connected in parallel. This connection only provides 1.5 volts, but with 4 amps of current. Experiment 5-1, voltage in series. In this experiment, you will demonstrate and observe how voltages add in series. The materials include 4 flashlight cells or D-types, 4 cell holders, and 1 multimeter. Step 1. Connect the 4 cells in series. See schematic in Exhibit 5-1A. Step 2. Set your multimeter to read voltages in the 0 volt to 10 volt range. Step 3. Measure and write down the voltage between the points A and B. Step 4. Measure and write down the voltages between points A and C. Step 5. Measure and write down the voltage between points A and D. Step 6. Measure and write down the voltage between points A and E. Do your results follow the formula for voltage sources in series? What conclusion can you draw from this experiment? Experiment 5-2, voltages in parallel. In this experiment, you will demonstrate and observe how voltages add in parallel. The materials include 4 flashlight cells, D-types, 4 cell holders, and 1 multimeter. Step 1. Connect the 4 cells in parallel. See the schematic in Exhibit 5-2A. Step 2. Set your multimeter to read voltages between 0 volt and 10 volt range. Step 3. Measure and write down the voltage between points A and B. Step 4. Remove cell number 4. Measure and write down the voltage between points A and B. Step 5. Remove cell number 3. Do not replace cell number 4. Measure and write down the voltage between points A and B. Step 6. Remove cell number 2. Do not replace cells number 3 and number 4. Measure and write down the voltage between points A and B. Do your results follow the formula voltage sources in parallel? What conclusion can you draw from this experiment? Sound navigation ranging, or sonar. Sonar is an underwater detection system based on horizontally directed sound waves and their echo reception. Sonar operates on a principle similar to that of radar, but instead of electromagnetic waves, it uses sound waves. There are 2 main types of sonar, passive and active. Passive sonar listens to sounds given off by possible targets and can determine the direction in which the object is located, but not its distance. Submarines generally use passive sonar systems because they do not give any sound that other sonar might detect. Active sonar sends sound waves through the water and receives echoes from any object struck by the ongoing waves. Most surface ships must use active sonar because noise from the ship itself interferes with passive sonar. Recall the familiar ping from the sonar in movies featuring submarines? This ping is an electrically produced sound featuring wave transmitted by a sonar transducer. The transducer uses a crystal and pulses of high frequency voltage to produce the vibration that is transmitted through the water. When the crystal is subjected to pulses of high frequency voltage, the crystal will distort at the same rate as the frequency. It is the crystal's distortion that produces the vibration. See the diagram at the bottom of page 92. The transducer is lowered through the bottom of the ship's hull, and sound waves are sent through the water at regular intervals in bursts. Electrical energy from light. Thanks to the United States space program, we can convert the sun's light directly into electricity. The invention of the photovoltaic cell, also called solar cell and photocell, made this conversion possible. The first photovoltaic cell was made from selenium, but today crystalline silicon is used. Photovoltaic cells made from crystalline silicon have a much higher efficiency than the original selenium cells. Photovoltaic cells, in figure 5-17, is constructed of 2 thin layers of crystalline silicon, each injected with impurities to form a negative and a positive semiconductor material. When secured together and then exposed to light, an electrical potential is developed. The layers are connected to thin wires that allow the photovoltaic cell to be connected to an electrical circuit. See figure 5-18. While a typical photovoltaic cell produces approximately 1 watt and 0.5 volts, the cells can be connected into arrays. Arrays consist of many cells connected in series and parallel to increase the voltage and current capabilities to a level sufficient to power lights and equipment. One application of power supplied by photovoltaic cells is power for a residential home. As a demonstration of this type of power, the Boston Edison Power Company built a model home powered by solar cells. The home is powered by 2 arrays of solar cells mounted on the roof. Each array contains 12 modules with 432 individual cells. The solar cells provide approximately 45% of the family's electricity. Today, solar cells are commonly used to partially power homes and heat swimming pools. The cells can also supply the complete power needs for items such as calculators, watches, and satellites. In addition, solar cells supply power for remote locations where there are no accessible power lines. See figure 5-19. Figure 5-20 shows a common solar array for providing power. Figure 5-19, solar-powered radio transmitter used for highway construction. See the top of page 96, figure 5-20, a solar array. 2026 update. Solar panels can routinely power an entire home,
but doing so effectively often requires a combination of properly sized array, battery storage for night usage, or grid-tied net metering. While possible, fully breaking free from the utility grid requires a significant investment in both panels and batteries to handle low sunlight days. Key considerations for a whole home solar include system sizing. A typical home requires about 20 to 25 high-efficiency panels, roughly 400 watts each, to cover an average of 10,000 to 11,000 kilowatt hours per year. Battery storage. To power your home at night, you will need battery storage, for example, lithium-ion, to store excess energy generated during the day. Net metering. Most homeowners stay connected to the grid using net metering to send excess energy to the utility company in exchange for credits used during cloudy days or at night. Factors affecting power include roof size, shading from trees or buildings, local climate, and energy efficiency of the home, for example, HVAC system, appliances, which determine how many panels are required. Off-grid challenges. While possible to go entirely off-grid, this requires a large, expensive battery bank and potentially a backup generator for extended low production periods. While equipment costs can range from $15,000 to over $25,000 before incentives for a full system, many homeowners find that it significantly reduces or eliminates electricity bills. As of 2026, standard residential solar panels typically provide from 400 to over 450 watts of power, with efficiencies ranging from 20% to over 24%. Monocrystalline panels, commonly used for homes, often exceed 22% efficiency, while premium models like the Maxion and Eco can reach nearly 25% efficiency.
Project 5-1, bottom of page 96, the photoelectric controller. Try building your own photoelectric control. A photoelectric control device using a photocell is diagrammed in the project schematic. When light shines on the cell, the resistance of the circuit changes. A cadmium sulfide photocell is a light variable resistor. It is most sensitive in the green to yellow portion of the light spectrum. With it, you can use light to control many electronic devices. Photocells are used in counting operations, burglar alarms, door opening mechanisms, and in many other devices. Experiment 5-3, building a thermocouple. In this experiment, you will demonstrate and construct a simple thermocouple. Materials: 1 piece of copper wire, 1 piece of iron wire, 1 pack of matches, and 1 multimeter. Step 1. Twist one of the copper wires together with one end of the iron wire. 2. Connect the leads of the multimeter to the opposite two ends of the copper and iron wire. Set the meter to read voltage. Be sure to observe the proper measuring technique. 3. Light a match and heat the junction of the two wires. 4. Observe the results on the meter. Explain what you have just observed. Could you use materials other than copper and iron? Photoelectric control. The same principle of generating electricity from light is used to produce a device called a photosensitive cell. Photoresistive cells are light-sensitive resistors. Instead of providing a direct supply of electricity, this device is used to vary the amount of current that can pass through it, much like a variable resistor would do. The photoresistive cell increases circuit resistance when there is no light. It decreases resistance when there is light. The symbol for a photoresistive cell is shown in figure 5-21. 5-22 shows a small thermocouple. Electrical energy from heat. A device used to indicate and control the heat of electric ovens and furnaces is shown in figure 5-22. This device is called a thermocouple. When two dissimilar metals in contact with each other are heated, a potential difference develops between the metals. Figure 5-23. In the demonstration of figure 5-23, an iron wire and a copper wire are twisted tightly together. Their ends are connected to a sensitive meter, such as a galvanometer. A galvanometer is a device that is capable of measuring very small currents. When the flame of a lit match heats the twisted joint, a reading on the meter can be observed. This indicates that an electromotive force is present.
Chapter 5 Review.
The conversion of chemical reaction in a battery is achieved by the voltaic
effect.
The cells create positive and negative ions and cause a potential difference between the electrodes, which develops voltage. There are primarily two types of battery cells. One is the primary, which is non-rechargeable, figure 4.9. And then there is the secondary cell, which is rechargeable, figure 4.10. The cells of batteries have changed greatly over the years, from dry cell to mercury cell, just to name a few. But the purpose and operation of the battery has not changed. All batteries contain acid and water, or what is known as electrolytes. It is imperative when you are mixing acid with water that you always pour the acid into the water so it does not splash back and burn you. Batteries will have a negative and positive post, and they are rated according to their voltage and capacity requirements. Capacity is the current a battery will produce over a period of time and is measured in ampere hours. Capacity of a battery really applies when you're talking about a car battery because of the need for starting amps. Batteries come in all shapes and sizes and can be used for large equipment like cars to some of the smallest like a pen light. Batteries give off voltage, therefore they can either be wired up in series or in parallel. In series, there's one path for current to flow and they are wired from negative to positive to increase voltage output, such as in figure 4.11. In parallel, all the positive cells are connected together and all of the negative cells are connected together to give a decreased voltage output but an increased battery life. Because batteries contain acid, the handling and disposal must be followed according to certain guidelines. The MSDS or Material Safety Data Sheets provide you with all of the pertinent information on how to handle hazardous material, from storage to harmful effects. This form will be provided by the manufacturer. As an electronics technician, you will mostly encounter small batteries used on circuit cards, which may control some type of indicator lights on a PLC, programmable logic controllers, and in almost all of your test equipment. Although batteries are the most familiar and common source of electricity, they are not the only source. Electrical energy can be generated from light through the use of a photovoltaic or photocell. A photovoltaic cell uses silicon injection into a material to create a negative and positive semiconductor material, and when exposed to sunlight, electricity is created. I only mentioned the photocells to give you a brief understanding before I moved on to the next topic, because you will not work on photocells.
As of 2026, electrical workers and electronic technicians routinely work on photovoltaic equipment, including solar panels, connections and wiring, and the equipment that work alongside photovoltaic modules. The photovoltaic industry is a significant part of world electrical production, which has experienced an almost exponential growth in the last 20 years. Many careers have developed from the photovoltaic field, and it remains one of the fastest growing careers.
The photoelectric controls are much more relevant to your study of electronics. The control is a light-sensitive resistor used to control current in electronic circuits, which is known as a photoresistive cell. Figure 4.13 shows an electronic diagram using a photosensitive resistor. You will find this used on a lot of outside lights. Once the sun goes down, the photosensitive resistor senses darkness. It will close a relay of some type to allow current to run to the light. Electrical energy can be created by heat. If you put two different metals together and heat them, the heat is then controlled and indicated by a thermocouple. You will find this configuration in radios and recording equipment. Electrical energy can be obtained from mechanical pressure by applying force to a crystal and causing distortion, therefore creating voltage. This is known as piezoelectric effect. The last three ways to create electrical energy are fuel cells, which are similar to batteries, magneto-hydrodynamic power generation, which is ionized gas passing through a magnetic field. It uses two plates to collect the gas. Those plates are called cathode negative and anode positive. Those two terms are associated with polarity throughout electronics. The easiest way to remember them is to think of letters of the alphabet. A comes before C, so A is positive and C is negative. Magnetism, which is a generator, converts the mechanical energy to electrical energy. We will discuss generators later because most electrical energy is produced from generators. They are also widely used as a backup power distribution throughout the world. They contain a multitude of electronic components that you will have to become familiar with and repair. Review questions, Chapter 5. How does the primary cell operate? Chemical action cannot be reversed. When two dissimilar materials are put in a reacting agent, like acid, they develop an electrical potential. Name 4 types of primary cells. Zinc carbon cell, the alkaline cell, the mercury cell, the lithium cell, and the silver oxide cell. Name 2 types of rechargeable secondary cells. Lead acid cell, nickel cadmium cell, nickel metal hydride cell. What are the advantages of a silver oxide cell? There are a few. Very stable discharge voltage, excellent high discharge characteristics, high energy density per unit volume, wide range of operating temperatures, and compact in size. Connecting cells in series increases their voltage rating, using the formula as shown. Name 2 types of rechargeable secondary cells. Lead acid cell and the nickel cadmium cell. Produces electricity from light. A photovoltaic cell. A light variable resistor is called a or an photoresistive cell. When 2 different metals are joined together and heated, they produce electricity. This is an example of an or a blank device. Thermocouple. A or an blank will produce electricity when pressure is applied to its surface. Piezoelectric effect. A or an blank converts sunlight directly into electricity. A photovoltaic cell. An ionized gas passes through a magnetic field and produces electricity. This form of electrical production is made by a or an blank device. Magnetohydrodynamic or MHD. Explain how a fuel cell works. 2 metallic electrodes are designed to allow hydrogen and oxygen gases to combine with the electrolyte of potassium hydroxide. The 2 metallic electrodes are a mean to allow the gases to combine with the electrolyte. Once the gases combine with the electrolyte, ionization occurs. The electrode attached to the oxygen line develops a positive potential. The chemical reaction in the fuel cell takes place when the gases combine with the potassium hydroxide. The ionization will continue as long as the 2 gases are supplied to the electrolyte. What is the polarity of an anode? Positive. Of a cathode? Negative. And you can remember that A comes before C. A is positive, C is negative, anode and cathode. Name 6 basic sources of electricity or electromotive force, EMF. Chemical reaction, your average battery. Light, photovoltaic from sunlight. Pressure, piezoelectric in your watch from a quartz crystal. Heat, like from a geothermal generator. Magnetic, as in your average generator, motor generator. Magnetohydrodynamic, and your fuel cell. What safety precautions should be taken when mixing acid and water? Always pour water into acid, never acid into water. Blank is a way of converting chemical energy into electrical energy, the voltaic cell. A cell that cannot be recharged is a primary cell. What is polarization? As a primary cell is used, hydrogen gas bubbles form around the carbon electrode, eventually forming an insulating blanket, increasingly reducing the terminal voltage of the cell. What is the major advantage of the nickel-cadmium battery? It is rechargeable, it has long life, high efficiency, compactness, and it's lightweight. Why is a low voltage detection circuit incorporated into electronic devices that are designed to use NIM batteries or NIMH batteries? It is because the polarity can be reversed if the battery is completely drained. In A or an blank connection, all positive terminals are connected and all negative terminals are connected. That would be a parallel connection. Remember, in a parallel connection, voltage remains the same and your amperage capacity increases. What is the composition of the electrolytes in a lead acid storage battery? It is sulfuric acid, H2SO4, and water, H2O. Check all that apply. Specific gravity can be measured with a hydrometer, can be used to determine the state of charge, and is the weight of a liquid as it compares to water. And all of these apply. What is the measurement of battery capacity? It is the ability to produce current over a certain period of time, and its measurement is the ampere hour, or AH. A or N blank is a device used to indicate and control the heat of electric ovens and furnaces. That is a pyrometer, which includes a thermocouple. What is the piezoelectric or piezoelectric effect? It is when electricity is generated from pressure